Hello, everyone. So last time we looked at the concept of functions and we had a quick review about the functions. And we know that, each function is a rule that assigns exactly one output to every input. And we looked at the concept of, one-to-one and onto functions. So last time, one-to-one and onto functions. So let's remind ourselves quickly about these concepts again. So one-to-one function means, mathematically, f is one-to-one if f is one-to-one, if f of a equals f of b, implies that a is equal to b for every a and b in domain of f. F is not one-to-one. F is not one-to-one if what happens? If there exists a and b in domain of f such that a is not equal to b, but f of a is equal to f of b. So if you can find two different inputs with the same output, then that means you have a repeated output and therefore your function will not be one-to-one. But if you want to show that it is one-to-one, then you cannot work with examples. You have to prove in general, meaning that if f of a is equal to f of b for any a and b in domain of f, then you have to be able to conclude that a is equal to b. And for onto, so f is onto, so let's just say f, say from a to b is onto or surjective if range of f is equal to the codomain, which is b. And equivalently, what does this mean? i.e., if for every b in b, there exists, let's say, a in a, such that f of a is equal to b. If every element in codomain occurs as an output, meaning that there is an input in the domain for which f of a is equal to b, in that situation, we can say that the function is onto or surjective because the range is same as codomain. And when can I say that it's not onto? So f from a to b is not onto if range of f is not equal to b. And when can I say that range of f is not equal to b? i.e., so if at least, because remember, codomain, when we have a codomain, range is always a subset of codomain. So that direction always holds. Now, however, codomain may or may not be a subset of range. So if it's not, then we say the function is not onto. So when can I say that the range is codomain is not a subset of range? If there exists at least one b, let's say, in the codomain, such that b does not belong to Rf. If at least one element in codomain is not included in the range, then the function is not onto. So let's look at an example. And before the example, let me also remind about bijection. When can I say that the function is bijection? F from a to b is called the bijection if f is both one-to-one and onto. If it's both one-to-one and onto, then we call the function a bijection. So let's look at an example. I think it's one of the book exercises, this example. Let f from z, z cross z to z, and f of m and n equals m minus n. So part A is f 1 to 1. Part B is f on 2. And part C is f bijection. So what do you think about this? So is f1 1 to 1? So 1 to 1 means, do we have a repeated output? Yes or no? But let's think about the outputs here. Let's think about some of the outputs. For example, well, the input here, or domain, elements of domain, are the elements which are of the form of a pair, ordered pair, where the first coordinate and second coordinate, both of them are integers. So for example, as 0 and 0 is one of the elements in the domain, and how much is the output corresponding to 0 and 0? Well, according to the definition of f of m and n is simply m minus n. So if I want to find f of 0 and 0, I just need to find 0 minus 0, and 0 minus 0 is 0. So 0 is one of the outputs. Now, is this output a repeated output, meaning that is there any other input whose output is also 0? Well, the answer is yes, there are so many more inputs whose outputs are 0. For example, what can you think? 1 and 1, let's say, right? F of 1 and 1 is also 1 minus 1, which is also 0. Or 2 and 2, and so on. So obviously for, but I gave 0 just as an example. So, but you could think about any other output. For example, 1 or 2 or 3. All these outputs also are repeated outputs, meaning that there are many inputs whose outputs are a fixed given number. So the answer to part A is no. No. We have, for example, f of 0 and 0 equals f of 1 and 1 equals 0, but 0 and 0 is not equal to 1 and 1. Once you show that there are two different inputs which have the same output, that would imply that the function is not 1 to 1. What about part B is f on 2? On 2 means, can I say that every element in codomain occurs as an output of f? Well, let's look at the codomain. Codomain is z. Can I say that every element in z occurs as an output? But again, to get an idea, let's think about some of the output, some of the elements in the codomain z. For example, 0 is one of the elements. Is 0 an output? Well, yes, of course, we just saw that 0 is an output, f of 0, and 0 is 0. What else? For example, 1. Is 1 an output? 1 is also an output because, for example, f of 2 and 1 is 2 minus 1, which is 1. Or, for example, 2. Is 2 an output? Yes, because, you know, for example, f of 3 and 1 is 3 minus 1, which is 2. And so on. So it seems that the function is on 2, but how can I justify it? Remember, if you want to show it is 1 to 1 or it is on 2, then you cannot rely on examples. You have to prove in general. If you want to show it's not 1 to 1 or not on 2, then you can rely on giving an example. So part B, my guess is yes, but if I want to justify, I cannot use examples. I have to prove in general. How can I prove in general? Well, I have to consider an element in the codomain. So let me say let, for example, let's say A in codomain Z. Now I have to show that this is one of the outputs. In other words, I have to find an input in the domain whose output is A. And what is A? A could be any integer. It could be 0, could be 1, could be 5, could be -5. I have to, that's why I'm saying that I have to prove in general. So I just consider some A in Z. It could be anything. Now, f of which input is A? F of m and n is m minus n. So if I want the result, the output or the result to be A, what should I consider as an input? Well, I have many options. One simple option is A and 0. Then f of A and 0 equals A minus 0 equals A. So that means, and A and 0 is in domain, right? Because is in Z cross Z. So that means A belongs to range of F. And that means F is onto. So I took an arbitrary element in codomain. I showed that at least one element in domain is going to be mapped to that element A, which means my function is onto. Now, did I have other choices other than A and 0? Here I considered A and 0 inside a domain, but did I have other choices other than A and 0? Well, yes. For example, what else, f of what else is 0? For example, if I say A plus 1 comma 1. A plus 1 comma 1, f of this is what? A plus 1 minus 1, which is also A. So I could consider, for example, A plus 1 comma 1 inside my domain as well. But it doesn't matter. You know, one element is enough. If you want to show that your element is in range, you have to find at least one element in domain which is mapped to the given element. One element is enough. It could be more. In this example, there are, in fact, infinitely many choices for each A, but one of them is enough. I just consider A and 0. You could consider A plus 1 and 1, or A plus 2 and 2, and so on. Okay, so the function is on two or surjective, but not 1-to-1. So is it bijection? So part C, the answer is no, since F is not 1-to-1 as shown in part A. All right. So this was one more example for the topics that we covered last time. Now let's look at the next subsection, 2.3.5. Some important functions. So in fact, we want to talk about floor and ceiling function. Floor and ceiling functions. So what is a floor function? What is a ceiling function? So definition, let X belongs to R, floor of X denoted by this notation is the largest integer less than or equal to X. Similarly, ceiling of x denoted by this notation is the smallest integer greater than or equal to x. So mathematically, if let's say x is bigger than or equal to n, less than n plus 1, for some integer n, then floor of x is equal to n. Similarly, if x is less than or equal to n, bigger than n minus 1, then again for some integer n, for some integer n, then ceiling of x is defined as n. So floor is the biggest integer less than or equal to x. Ceiling is the smallest integer greater than or equal to x. Now, in our notation, mathematical notation, if x is bigger than or equal to n, less than n plus 1, then the largest integer less than or equal to x is n, because obviously n is less than or equal to x according to the assumption, and is the largest one among the integers that are less than or equal to x. N is the largest one. Why? Because, for example, let's say n minus 1 is also less than x. If x is bigger than or equal to n, but n minus 1 is less than x, for example. But n minus 1 is not the largest integer bigger than or equal to x, because n is also less than or equal to x and is larger than n minus 1. And so on. So in this case, floor of x is n. Similarly, in the other case, ceiling of x is also n, if x is less than or equal to n, bigger than n minus 1. Let me give you an example, maybe you understand better. So for example, let's say floor of 2.3. What is floor of 2.3? Floor of 2.3, according to the definition, a floor of a number is the largest integer less than or equal to x. But which integers are less than or equal to 2.3? 2 is one of them, right? 2 is less than 2.3. What else? 1 is one of them. 0 is one of them. Minus 1 is one of them, and so on. But among these integers that are less than x, minus 1, 0, 1, 2, which one is the largest one? The largest such integer is 2. 2 is the largest integer less than or equal to 2.3. Two is largest integer less than or equal to 2.3. What about floor of minus 1.5? Again, let's think about it. Which integers are less than minus 1.5? Think about the real line. Which integers are less than minus 1.5? Well, minus 2 is one of them, minus 3 is one of them, minus 4 is one of them, and so on. Among these integers, which one is the largest one? The largest one is minus 2. So floor of minus 1.5 is minus 2, but floor of 2.3 is 2. Usually for the floor of positive integers, there is no confusion. But for negative integers, some students get confused. because for positive integers for 2.3, we said 2. So for minus 1.5, many people would think minus 1, but that's not the case. We have to look at the definition. The definition says the largest integer less than or equal to x. Well, it cannot be minus 1 in the case of minus 1.5, because minus 1 is not less than minus 1.5, it's bigger than minus 1.5. We have to choose among the integers that are less than or equal to x, we have to choose the largest one. And minus 1 is not one of those integers in this case. Minus 2, however, is one of them and is the largest one. What about this ceiling? Again, similarly, ceiling of 2.3 is 3, right? Again, you have to look which integers are bigger than 2.3, choose the smallest one. 3 is bigger, 4 is bigger, 5 is bigger, and so on. The smallest one is 3. And ceiling of minus 1.5 similarly is minus 1. We have to again see which integers are bigger than minus 1.5. Well, minus 1, 0, 1, 2, and so on. And which one is the smallest one? Minus 1 is the smallest one. Okay. What about the graphs? For floor function, well, first we have to think about the domain. What is the domain of floor function? Well, domain means the inputs. Inputs come from which set? Again, let's look at the definition. Definition says let x belongs to R. So for any x belongs to R, we define the floor of x. That means x is allowed to be any real number. So domain is all real numbers. And then we can look at the graph. So if x is between 0 and 1, floor of x is 0. Right? The floor of x is equal to 0 if x is between 0 and 1. For real numbers x, which are between 0 and 1, for example, 0.1, 0.2, 0.3, 0.9, for those real numbers, the floor is 0, the output is 0. Y equals 0. Y equals 0 means x-axis, right? So on this part of x-axis between 0 and 1, the y value is also 0. What about between 1 and 2? Between 1 and 2, the y value, the output is 1. For example, x equals 1, 1.1, 1.2, right? The floor is 1. Okay, so I'm looking at inputs and outputs. If the input between 0 and 1, the output is 0. So y equals 0, a horizontal segment. Now, which part is filled, which one I have blank hole? But I have to be careful about boundary points. At 0 itself, the output is 0. So that's why here you can see the filled point. Here is the filled point. But at 1, at x equals 1, the output is not 0 anymore, it's 1. So that's why I have a blank hole here and a filled point here. Similarly at 2, again, the output is not 1 anymore. So I have a jump here. Fill 3, and this would be 2. And so on. Similarly on this direction also, I have -1 here. And then I have -2 here, and so on. Okay. So for ceiling, let me leave as exercise. So exercise, sketch the graph of ceiling of X. Okay, now let's look at some properties of floor and ceiling properties. Okay, the properties are mentioned in your book. So it's in page 159. But let's look at a few of them. So for example, say A, X minus 1 is less than floor of X, less than equal to X, less than equal to ceiling of X, less than X plus 1. Part B, floor of minus X is minus ceiling of X. Ceiling of minus X is minus floor of X. Part D, floor of X plus N is equal to floor of X plus N for any integer N in Z. And part E, ceiling of X plus N is equal to ceiling of X plus N, again for any N belongs to Z. Okay, let's look at the proof of at least one of these properties, and then I can leave the rest as exercise. For example, it's a part B. Let's look at the proof of part B. So we want to show that floor of minus X is equal to minus ceiling of X. Okay, so how can I prove this? Well, let's start with, well, we know that each X, for every X, we can assume that if you look at the definition of floor, the mathematical definition, we said that if X is bigger than or equal to N, less than N plus 1, then floor of X is defined as N. So for every X, there exists an integer N that X is bigger than or equal to N, less than N plus 1. So let N is Z be the unique number. So there is only one number with this property, right? There be the unique number such that X is bigger than or equal to N, less than N plus 1. Or maybe I can start with the other form that says X is less than or equal to N, bigger than N minus 1. For every X, there exists one integer. We see if you look at the definitions that we have, for every x, there exists a unique integer n that x is bigger than or equal to n less than n plus 1. Similarly, there exists a unique integer, you can call it n again, or you can call it m, that is greater than equal to, less than equal to m, and x is less than equal to m and bigger than m minus 1. Why there exist such integers? Maybe we don't want to go into details of proof of existence of such integers, but just accept the intuitive reason that for every x, there exists always a largest integer less than equal to x, which we call it floor. For example, 2.3, the largest integer is 2. There exists such integer, right? Less than equal to 2.3. Or for 5.6, the largest integer less than equal to 5.6 is 5, and so on. So there exists always such integer, which we call it floor. So floor always exists. Similarly, ceiling always exists. Okay, so my starting point could be, it's up to me. I can start with an integer n satisfying this property. I can start with an integer n satisfying this property, or I can start with an integer n satisfying this property. But here, I'm going to start with an integer n satisfying this property. Why? Because if you look, I have to look at what I want to show. What do I want to show? I want to show that floor of minus x is minus ceiling x. So I'm going to take floor of minus x, not x itself. If I wanted to take floor of x, then I would start with my starting point. I would choose it as this one, because for this one, I can easily take floor, and floor will be n. But I'm going to here, and here I'm going to take a ceiling from x itself. Look at the property I want to show. I want to take ceiling from x itself and floor from minus x. So therefore, I'm going to start with this type of inequality so that I can easily take ceiling of x. What is ceiling of x? Then ceiling of x would be equal to n by definition of ceiling, right? That was exactly the definition of ceiling, that if x is between n and n minus 1, then the ceiling would be defined as n. And what about the floor of minus x? And so if I multiply everything with minus n minus 1 becomes bigger than minus x, bigger than equal to minus n. When you multiply an inequality with a negative number, inequality flips. And this means minus n less than equal to minus x less than minus n plus 1. I can also write this inequality this way, right? It doesn't matter if you say 5 is bigger than 2, or you can say 2 is less than 5. So, of course, I can also write here, it says minus n less than equal to minus x less than minus n plus 1. Minus bracket n minus 1 is minus n plus 1, which is what I wrote here. And ceiling of a floor of minus x is what? Thus, floor of minus x equals minus n. Again, by definition of floor. See, in part B, I want to calculate floor of minus x and compare it with ceiling of x. I started with this inequality. I calculated ceiling of x. Now floor of minus x will be minus n. Why? Because minus x is bigger than or equal to minus n less than minus n plus 1. But definition of floor was exactly saying this, that if x is bigger than or equal to m, let's say less than m plus 1, then this number here would be considered as floor. But here my m is minus n. So floor of minus x is minus n. Well, I'm done. Ceiling of x is n. floor of minus x is minus n. So let me call this one star. This one I call it star. This one I call it 2 star. Now star and 2 star combined imply that floor of minus x is equal to minus ceiling of x equals minus n. Floor of minus x is minus n, that's 2 star. Star says ceiling of x is n. But I want to compare floor of minus x. I'm doing part B. Floor of minus x with minus ceiling of x. So if ceiling of x is n, minus ceiling of x will be minus n, which means it's the same as floor of minus x. So these two are equal and both are equal to minus n. Well, the fact that both are equal to minus n, and that part I don't need it. I just want to show that floor of minus x is minus ceiling of x. And these two are equal because both of them are equal to minus n. So this was proof of part B, proof of other parts. This one let me leave as exercise. Okay, let's look at another example. Let x be any real number. Show that floor of 2x is equal to floor of x plus floor of x plus 1/2. Well, here, we are talking about floor, so you could guess that you may want to, start with the inequality x bigger than equal to n less than n plus 1, which is the one that I said, we can use to start as a starting point for the floor questions. But then in this question, because we are talking about floor of 2x as well, now if I multiply everything by 2 here, what do I get? I'll get 2x bigger than 2n less than 2n plus 2. So what would be the floor of 2x? If 2x, we know it's between 2n and 2n plus 2. Well, I cannot find the floor of it. Because to find the floor, basically, I have to look at the definition of floor. What is the form of the inequality that I need? I need to have x be put between two consecutive integers. It's important that you put x between two consecutive integers. We can call one of them n, then the other one n plus 1. But when you have 2n and 2n plus 2, you don't have consecutive integers anymore, right? Because if one of them is 2n, the other one has to be 2n plus 1, not 2n plus 2. So how can we fix this issue? Well, why is this plus 2 appeared? Because this plus 1 was multiplied by 2. Well, how about if because when x is between n to n plus 1, well, that's because I'm going to multiply it by 2. This range is too big to help us understand the floor of 2x. If x is between n and n plus 1, means either, so if you look at the real line, let's say this is n, this is n plus 1, this gap is too big. But if I divide this into 2 parts, from n to n plus 1/2, and then plus n plus 1/2 to n plus 1, then that gap is small enough to help me realize or understand or calculate the floor of 2x. So again, the idea is that this gap between n to n plus 1 is too big. I won't be able to calculate floor of 2x. But if I divide this gap into 2 smaller gaps, then I can fix this issue. So how can I write my proof then? I explained the idea. Now the solution or proof. So I can say let x because n plus, let's say epsilon. Remember we said that is x between n to n plus 1/2, or is it between n plus 1/2 to n plus 1? So I can write it as x equals n plus epsilon with epsilon bigger than or equal to 0 less than 1. Now I can consider two cases. Remember two small gaps, if x is between first small gap, or is it in the second small gap? So case 1, if epsilon is bigger than or equal to 0 less than 1/2. Then what can I say about 2x? Then x is bigger than or equal to n less than n plus 1/2, right? Because x is n plus epsilon and epsilon is less than 1/2 by my assumption in case 1. So then if I multiply by 2, 2n less than or equal to 2x less than 2n plus 1. So how much is floor of 2x? Floor of 2x would be 2n. Because now 2x is put between two consecutive integers, 2n and 2n plus 1. Therefore, I can say that the floor is 2n. So the left-hand side is 2n. Remember, I want to show this identity. Left-hand side I show is 2n. Now, if I calculate the right-hand side and show that right-hand side is also 2n, then I'm done. So first I need, for calculating right-hand side, first I need floor of x. Now, so this means left-hand side is equal to 2n. Now for right-hand side, what is floor of x? Well, x is between n to n plus 1/2. So floor of x, remember for floor of x, x has to be put between two consecutive integers, but it is already between two consecutive integers, n and n plus 1. Remember about the real line again, n plus 1, n plus 1/2. Well, if x is here, of course, x is in the bigger gap as well, right? So x between, if it's less than n plus 1/2, is of course less than n plus 1 as well. So floor of x would be n. What about, I also need floor of x plus 1/2. So first let's calculate x plus 1/2. So also, if I add with 1/2 everything, n plus 1/2 less than or equal to x plus 1/2 less than n plus 1. Using, let me say 1 above. Let's call this one 1. Okay, if I add 1/2 to this inequality, I'll get n plus 1/2 less than x plus 1/2 less than n plus 1. So what is floor of x plus 1/2 then? So x plus 1/2 is going to be bigger than n less than n plus 1, right? See, if x plus 1/2 is in the second gap, look at the second gap, x plus 1/2 will be here. So if x plus 1/2 is here, in the second gap, of course, it will be in the bigger gap as well. So x plus 1/2 will be between n and n plus 1. Once it's put between two consecutive integers, I can conclude that the floor of it is n. So what can I say about the right-hand side then? So that's right-hand side is equal to floor of x plus floor of x plus 1/2. The first integer, the first number was n, the second one was n as well. The answer is 2n, which is equal to the left-hand side. So we are done with case 1. Now case 2. So if epsilon is bigger than equal to 1/2 less than 1. Then what can I say about 2x? So remember x was n plus epsilon. So then that means x is bigger than equal to n plus 1/2 less than n plus 1, right? Because epsilon is bigger than 1/2, so n plus epsilon bigger than n plus 1/2. And if I multiply by 2, 2x bigger than 2n plus 1 less than 2n. So in this case, left-hand side, which was floor of 2x, will be 2n plus 1. Now I have to show the right-hand side is also 2n plus 1, and then I can say that again, they are equal. Now for right-hand side, what can I say about the floor of x first? Floor of x will be n, right? Because x is between n and n plus 1. My assumption is x is in there. Here, if you look at the real line again, n plus 1, n plus 1/2. Now my x is here in this case. So if x is here in the second gap, of course, again, is in the bigger gap. So floor of x is n. What about x plus 1/2? You can see x is between n plus 1/2 to n plus 1. So if I add with 1/2, n plus 1 will be less than x plus 1/2 less than n plus 3/2. So floor of x plus 1/2 will be how much? X plus 1/2 will be between n plus 1 to n plus 3/2. So less than n plus 2 basically, right? Because where is n plus 3/2? N plus 3/2 would be somewhere here, which is less than n plus 2. So x plus 1/2 will be here in this case, which is between n plus 1 to n plus 2. So floor of it would be n plus 1. So in this case, right-hand side, which is floor of x plus floor of x plus 1/2, and that's n plus 1 equals 2n plus 1, which is equal to my left-hand side. Okay, another example, true or false. Floor of x plus y is equal to floor of x plus floor of y for any x and y in R. So this one, do you think is true or false? If it's true, we have to, of course, prove in general. If it's false, we can come up with a counter example. So after a little bit investigation, always if you want to know something is true or false, the very first step, you can think about some examples to help you get some idea. You can try some x and y values and get the idea of what the left-hand side is, what the right-hand side is. And you'll see that we can construct a counter example. So the answer is false. Counter example. Let x equals y equals 1/2, both of them 1/2. Then x plus y would be how much? X plus y, floor of x plus y, left-hand side would be floor of 1/2 plus 1/2. Floor of 1/2 plus 1/2 means floor of 1, which is 1. But right-hand side will be floor of x plus floor of y, with floor of 1/2 plus floor of 1/2. And that's 0 plus 0, which is 0. And these two are not equal. So that means the statement is false. Okay, so another example. So this one is question 45. Question 45. This section, 2.3, same section. So let g of x equals floor of x. Part A, find g inverse of 0. So what is g inverse of 0? G inverse of the set 0. So if you remember last time we discussed this, that do we talk about f inverse of a number or f inverse of a set? If it's f inverse of a number, first of all, your function has to be invertible, meaning that it has to be 1-to-1. And then you can find f inverse of the number. But in this case, the floor function is not 1-to-1, right? Because remember the graph, it obviously does not pass the horizontal line test. Look at the graph here. The horizontal segments, right? So obviously it doesn't pass the horizontal line test. So it's not 1-to-1, therefore not invertible either. But here it's not talking about G inverse of 0, element 0. It talks about G inverse of set 0. G inverse of a set can be defined even if the function is not 1-to-1. How did we define f inverse of a set? All the elements in the domain whose outputs are inside our set. Here my set has only one element 0. So G inverse of 0, set 0 is going to be all elements inside domain whose outputs are 0. So this is by definition so this is G inverse of 0 is going to be all elements x in R such that G of x, which means floor of x, is inside this set. Inside this set means 0. So all elements x in the domain whose outputs are 0. Well, let's look at the graph. Let's see which inputs, which x values have output of 0. Here. These are different outputs here, right? 0, 1, 2, -1, -2, and so on. Which inputs have output of 0? Only the elements between 0 and 1, right? The first segment here, this segment. Elements in this segment have output 0. So that means all the inputs greater than equal to 0, less than 1. So this is simply elements between 0 and 1. Because for any x between 0 and 1, we have floor of x equals 0. So part B, G inverse of -1, 0, 1. Let me leave this as exercise. Part C, G inverse of this set. So a set of elements x such that x is bigger than 0, less than 1. So again, according to the definition of G inverse of a set, this means all elements x in R such that G of x, which is floor of x, belongs to, so the output must belong to this set. All the inputs whose outputs belong to this set. This set means what? Open interval 0 to 1. So all the inputs whose outputs belong to open interval 0 to 1. So which inputs have their outputs belong to this set? Let's think about it. For example, 0. What is the output for 0? It's 0 itself. It's not inside this set because it's open interval. 0.1, for example. What is the output for 0.1? The output for 0.1 is also 0, and again, 0 is not in this this set open interval. 0.6, again, the output is 0, it's not in here. 1, if the input is 1, output is also 1, it's not inside this set. 1.2, again, the output is 1, is not inside this set. So this set, as you can guess, is empty set. And I can justify it by saying that the output of floor X is always an integer and cannot be inside 0 to 1. We are looking for inputs whose outputs belong to the open interval 0 to 1. But every number in open interval 0 to 1 is non-integer. Every element in the open interval 0 to 1 is non-integer. So the output of floor, none of them can be an output for floor X, because the output for floor X is always an integer, but none of the elements here is an integer. Therefore, this set must be the empty set.